Hello, and welcome to tonight's Space Sleep Story. If you appreciate what we do here, please like or subscribe for future relaxing nighttime space journeys. Tonight, we embark on a voyage to Lagrange Point 2, 1.5 million kilometers beyond Earth, where the James Webb Space Telescope extends humanity's vision 13 billion years into the past. So settle into your most comfortable position, close your eyes, and prepare for a contemplative journey aboard the most powerful eye humanity has ever placed among the stars. Before we begin, let us prepare your body and mind with gentle breathing. Take a slow, deep breath with me now. Inhale gently for 4 counts. Hold the peace. Exhale for 6. Feel your body releasing into stillness. Let tension drain from your shoulders, your jaw, your hands. With each breath, you become more present, more calm, more ready for rest. Another gentle breath as we continue our preparation. This time, notice how your chest rises and falls, a rhythm as ancient as life itself. Breathe in the vastness of space. Hold this peaceful moment. Breathe out everything that no longer serves you. Feel the stress of the day leaving your body with each exhale. With each breath, you release a little more into relaxation. We arrive now at a remarkable point in space, a location where gravitational forces achieve perfect balance. Lagrange Point 2 sits approximately 1.5 million kilometers beyond Earth, 4 times the distance to the Moon. Here, Earth's gravity and the Sun's gravity combine with centrifugal force to create a stable position where spacecraft can orbit with minimal fuel expenditure. This is where Webb watches the universe, floating in perfect gravitational equilibrium, maintained in position by the delicate mathematics of celestial mechanics. Webb does not remain stationary at this point, but follows what astronomers call a halo orbit. Picture an elliptical path approximately 800,000 kilometers wide, circling the invisible balance point like a graceful dance. Webb completes one circuit every 6 months, moving through space in a carefully choreographed motion. This orbit prevents Earth and Moon shadows from blocking sunlight needed for solar panels, while maintaining thermal stability. Constant orientation, constant temperature, constant watching. The telescope's position offers profound advantages for observation. From here, Earth, Sun, and Moon remain in the same direction relative to the telescope, allowing the Sunshield to block all 3 heat sources simultaneously. Unlike satellites orbiting Earth, experiencing day-night cycles every 90 minutes, Webb maintains continuous communication with ground stations via the Deep Space Network. No orbital blackout periods, no thermal cycling, no interruptions to the patient work of collecting ancient light. Just steady, continuous observation of the cosmos. Webb launched on Christmas Day, December 25th, 2021, beginning a journey that would take 1 month to complete. The transit covered 1.5 million kilometers, much slower than Apollo missions due to gravitational considerations and the need for mid-course corrections during deployment. Engineers watched every kilometer with held breath. On January 24th, 2022, Webb reached its destination and began the work it was designed for 30 years to accomplish. Now it watches, collects, reveals what has been traveling toward us since the universe was young. Webb carries enough hydrazine fuel for orbital maintenance and momentum management to operate for a minimum of 10 years. But if fuel consumption remains efficient, the mission could last 20 years or more. Each thruster firing is precisely calculated to avoid contaminating the delicate gold-coated mirrors with exhaust. The telescope must remain pristine, uncontaminated, perfect in its optical precision. Years of careful operation stretch ahead. Years of discovery. Years of humanity learning what happened in the cosmic dawn. As we approach Webb from a distance, it appears unlike any spacecraft you have seen before. Imagine a geometric flower made of gold and silver, unfolded against the black of space. 18 hexagonal mirror segments form the primary reflector, each coated in gleaming gold that catches starlight from the universe's beginning. A secondary mirror, suspended on a long boom, extends forward. Behind the golden mirrors, 4 scientific instruments cluster together, each one a masterpiece of cryogenic engineering. And below, the massive Sunshield stretches like a silver sail. The primary mirror measures 6.5 meters in diameter, nearly 3 times larger than Hubble's 2.4-meter mirror. Light gathering capability increases with area, not diameter, so Webb collects 6.25 times more light than its predecessor. More light means fainter objects become visible, more distant galaxies reveal themselves. Earlier epochs of cosmic history open to human perception. This mirror makes possible observations that Hubble could never achieve, no matter how long it stared into the darkness. A new window on reality, wider and clearer than any before. A single 6.5-meter mirror proved impossible to launch. No rocket fairing could accommodate such a massive structure. Engineers solved this challenge through segmentation, dividing the mirror into 18 hexagonal pieces, each 1.32 meters from point to point. These segments folded for launch like flower petals closed, then deployed in space, unfolding in a carefully rehearsed sequence. What was compact became expansive. What was protected became exposed. What was potential became actual. The flower opened, and humanity's vision extended 13 billion years into the past. Each segment required exceptional precision. Made of beryllium, a metal chosen for its strength, light weight, thermal stability, and ease of precision machining. Every segment was coated with microscopically thin gold, approximately 100 nanometers thick, about 1/1000th the width of a human hair. Gold was selected for its exceptional infrared reflectivity, 98% or higher in Webb's target wavelengths. Gold does not corrode or tarnish in the space environment. For decades to come, these golden mirrors will reflect the universe's most ancient light without degradation. But creating 18 perfect segments was only the beginning. They must be aligned to function as a single mirror, aligned within wavelengths of light to achieve the optical precision necessary for revolutionary discoveries. Each segment has 7 actuators that adjust position in 6 directions: piston, tip, tilt, XY translation, and radius of curvature. 126 actuators in total maintain nanometer precision despite temperature fluctuations and the stresses of the space environment. Active alignment operates throughout the mission's life, continuously perfecting what is already nearly perfect. Wavefront sensing systems monitor mirror alignment continuously. Sensors analyze stellar images, detecting aberrations smaller than the wavelength of light itself. When imperfections are detected, commands flow to actuators, adjusting positions by nanometers, restoring optical perfection. No human hand touches these mechanisms. Everything is commanded remotely from Earth. Adjustments made across 1.5 million kilometers of space, based on photons collected from objects billions of light years distant. Precision achieved through mathematics, engineering, and patient observation. Webb observes the universe in infrared wavelengths from 0.6 to 28.5 microns. These wavelengths are far longer than visible light, which spans only 0.4 to 0.7 microns. Infrared vision allows Webb to penetrate cosmic dust clouds that block visible light completely. It can observe extremely redshifted distant galaxies, whose light has been stretched by the universe's expansion during its 13.8 billion year journey. What is invisible to human eyes and optical telescopes becomes clear in infrared. A hidden universe revealed. The universe's expansion stretches light from distant galaxies toward longer wavelengths, shifting visible light into the infrared. The most distant galaxies, those 13 billion light-years away and more, are shifted entirely beyond the visible spectrum. Optical telescopes cannot see them at all. But for Webb's infrared instrumentation, these ancient galaxies appear clearly. Their light, emitted when the universe was only a few 100 million years old, arrives now in wavelengths perfectly matched to Webb's capabilities. What Hubble could not see, Webb observes routinely. To observe infrared light from cosmic sources, Webb's instruments must remain colder than the objects they study. Otherwise, the telescope's own heat creates noise that overwhelms faint cosmic signals. Webb's instruments operate at approximately 40 Kelvin, -233 degrees Celsius. The mid-infrared instrument, MIRI, is cooled even further, to 7 Kelvin, -266 degrees Celsius, using an active mechanical cryocooler. Colder than most of outer space itself, cold enough to hear the universe's faintest whispers. The Sunshield makes these cryogenic temperatures possible. 5 layers of Kapton membrane, each the thickness of a human hair, stretch across a frame measuring 21.2 by 14.2 meters, approximately the size of a tennis court. The layers are separated by vacuum gaps, and collectively they provide sun protection equivalent to SPF 1 million or more. On one side, sunlight heats the membrane to 85 degrees Celsius. On the other side, just meters away, the temperature remains -233 degrees Celsius. A 300-degree differential across a structure you could puncture with your finger. Unlike some previous infrared telescopes that required expendable cryogen coolant, limiting their operational life to months or years, Webb uses passive radiative cooling. The Sunshield blocks heat from Sun, Earth, and Moon. The telescope's cold side radiates heat into space. Operational temperatures are achieved without consumables, except for MIRI's mechanical cryocooler. This design enables decades of observation, not mere years. Webb can watch the universe change over human timescales, tracking phenomena that unfold across across decades. Patient observation matching cosmic patience. Four scientific instruments collect and analyze the ancient light that Webb's mirror gathers. NIRCam, the near-infrared camera, detects wavelengths from 0.6 to 5 microns, providing the stunning deep-field images that have captivated humanity. NIRCam also serves as the wavefront sensor for mirror alignment, a dual role requiring exceptional precision. It is equipped with coronagraphs that block starlight, allowing observation of exoplanets orbiting close to their parent stars. One instrument performing multiple critical functions, maximizing scientific return from every component. Marcia Ricci led the team that developed NIRCam over more than 20 years. She recalls the moment first images arrived. When first images came down and NIRCam worked perfectly, revealing galaxies from cosmic dawn exactly as we'd hoped, I cried. 2 decades of my life validated in those first photons. Imagine dedicating 20 years to building an instrument you could never repair if something went wrong. No second chances at Lagrange Point 2. And then watching it exceed every expectation, revealing what you dreamed it would reveal. NIRSpec, the near-infrared spectrograph, analyzes light from 0.6 to 5.3 microns, breaking it into component wavelengths to reveal chemical compositions. Its most revolutionary feature is the micro-shutter array with 250,000 programmable shutters, each measuring 100 by 200 microns. This array allows simultaneous observation of more than 100 objects at once, a game changer for galaxy surveys. What once required hundreds of separate observations can now be accomplished in a single exposure. Efficiency multiplied, discovery accelerated. MIRI operates at the longest wavelengths, 5 to 28.5 microns, in the mid-infrared range. It is the coldest instrument aboard Webb, maintained at 7 Kelvin by a pulse tube cryocooler. MIRI observes the coolest phenomena: protoplanetary disks where planets are forming, newly forming planets still glowing with the heat of their creation, distant galaxies whose star formation is obscured by dust. What is hidden from every other instrument reveals itself to MIRI. The coldest detector, seeing the coolest objects, extending observation to phenomena previously beyond reach. Canada contributed the fine guidance sensor and near-infrared imager and slitless spectrograph, FGS, NIRIS. The fine guidance sensor provides precision pointing with accuracy of 0.007 arcseconds, like detecting a baseball 150 kilometers away. Without this precision, observations would blur, faint objects would be lost, discoveries would remain unmade. NIRIS specializes in characterizing exoplanet atmospheres and studying weak gravitational lensing effects. International collaboration, each nation contributing unique expertise, combining to extend human knowledge beyond any single country's capability. Webb spectrographs resolve light into component wavelengths, creating spectra that reveal chemical compositions of distant objects. When an exoplanet transits in front of its star, starlight filters through the planet's atmosphere. Different molecules absorb specific wavelengths. The resulting spectrum reveals what gases are present: water vapor, carbon dioxide, methane, perhaps organic molecules. For the first time in human history, we can analyze the atmospheres of worlds orbiting other stars. We can ask, does that planet have water? Does it have the chemistry necessary for life as we understand it? Questions that were science fiction now become science. Webb can observe objects 10 to 100 times fainter than Hubble's detection limit. This sensitivity enables detection of the first galaxies that formed 100 to 250 million years after the Big Bang, 13.6 to 13.7 billion years ago. We are pushing observation into the cosmic dawn era, when the universe transitioned from dark ages to a star-filled cosmos. The earliest structures, the first galaxies, the primordial star formation, epochs once accessible only through theoretical models, are now observed directly. Theory meets reality, and reality proves more complex, more interesting, more beautiful than anyone predicted. On Christmas Day, 2021, an Ariane 5 rocket lifted off from Kourou in French Guiana. The launch site was chosen for its equatorial location, which provides additional velocity from Earth's rotation, and for the partnership with the European Space Agency. The launch was nearly flawless, with precision so high that it conserved fuel, extending Webb's mission life estimate beyond the original 10 years. Decades of preparation, billions of dollars of investment, thousands of people's careers, all committed to that moment. And it worked. The rocket performed beautifully, beginning Webb's month-long journey to L2. What followed was the most complex spacecraft deployment sequence ever attempted. 344 single-point failures any one of which would be catastrophic. No possibility of repair at Lagrange Point 2. Paul Geithner, Deputy Project Manager, recalls, "Those 30 days of deployment, I barely slept. Every successful step was relief mixed with dread of the next step. When the final mirror segment locked, I felt a decade of tension release. Step by step, day by day, the world watched as Sunshield unfolded, mirror segments deployed, secondary mirror extended. Each milestone celebrated with exhausted joy." Crystal Puga, lead spacecraft systems engineer, focused on the Sunshield. The Sunshield is insane engineering. 5 layers, each precisely separated, unfolding in specific sequence, every membrane tensioned perfectly. 107 release mechanisms. If one fails, the whole mission fails. 107 opportunities for disaster. 107 perfect executions. The Sunshield unfolded over several days, each step watched by engineers who had rehearsed the sequence thousands of times on Earth, but could never perfectly simulate space. When the final membrane tensioned and the Sunshield took its full shape, relief swept through mission control. Lee Feinberg managed the optical telescope element, including mirror alignment. He describes the process. Aligning 18 mirror segments to act as a single surface in space at cryogenic temperatures. It's like assembling a watch while wearing oven mitts. The actuators adjust in nanometers. We can't physically touch anything. The first time the team aligned all segments and produced a sharp stellar image, they knew they had accomplished something historically significant. What had been 18 separate reflections became one perfect image. Potential became achievement. On July 12, 2022, NASA unveiled Webb's first full-color images to the world. A deep field showing thousands of distant galaxies, some forming when the universe was a mere fraction of its current age. The Carina Nebula, revealing starbirth in unprecedented detail. Protostars glowing through dense clouds. The Southern Ring Nebula, showing a dying star's beautiful shells of expelled material. Stephan's Quintet, a group of 5 galaxies locked in gravitational dance. A spectrum from exoplanet WASP 96b, showing detailed atmospheric composition. 30 years of development validated in these first revelations. Within 6 months of beginning science operations, Webb had collected data addressing all 3 primary mission goals. How did the first stars and galaxies form? Observations revealing massive structured galaxies at redshift 13 and 14 farther than any previous detection. How do galaxies evolve? Detailed images showing galactic mergers, star formation rates, supermassive black hole growth across cosmic time. How do stars and planetary systems form? And where are the ingredients for life? Infrared views penetrating stellar nurseries, protoplanetary disk imaging, exoplanet atmosphere characterization, detecting water, carbon dioxide, complex molecules. Unprecedented scientific return on 3 decades of investment. Jane Rigby, Operations Project Scientist, reflects on early galaxy detections. We're seeing galaxies at redshift 13, 14, light from just 200 to 300 million years after the Big Bang. These galaxies are more massive, more structured than our models predicted. Models developed over decades, refined through generations of observations, suddenly confronted with reality more complex than theory anticipated. These early galaxies shouldn't exist in the forms observed, yet there they are, demanding explanation. Webb is already rewriting galaxy formation theory in its first year, overturning decades of assumptions. The pillars of creation, imaged famously by Hubble in visible light, were re-observed by Webb in infrared. Natalie Battaglia, astrophysicist, describes the revelation. Hubble showed us the pillars, iconic image of towering dust clouds. Webb showed us inside the pillars, hundreds of newly forming stars invisible to Hubble, protostars glowing in infrared. Every star forms surrounded by dust. Visible light cannot penetrate those dense cocoons. Infrared wavelengths pass through, revealing stellar birth in detail never before observable. Not just prettier pictures, but new understanding of how stars come into being. In September 2022, NIRS detected carbon dioxide in the atmosphere of WASP 39b, a hot Jupiter exoplanet 700 light-years distant. Klaus Pontoppidan, project scientist, recalls the moment. First definitive CO2 detection. That single observation proved Webb can characterize exoplanet atmospheres. Now we're targeting potentially habitable worlds. We might detect biosignatures in my lifetime. The detection of carbon dioxide was just the beginning. Webb has since characterized multiple exoplanet atmospheres, detecting water vapor, clouds, temperature structures, chemical compositions. We are learning what other worlds are made of. Webb exploits gravitational lensing, using massive galaxy clusters as natural telescopes. The gravity of these clusters bends and magnifies light from more distant galaxies beyond them, revealing objects otherwise too faint to detect. The technique allows observation of the universe's earliest structures, galaxies that formed when the universe was younger than 200 million years old. Nature provides the magnification, Webb provides the sensitivity and resolution, and together they reveal cosmic dawn, transitioning from darkness to light. The first stars igniting, the first galaxies assembling, the universe awakening. Mid-infrared observations identify complex organic molecules in interstellar dust clouds. Polycyclic aromatic hydrocarbons, carbon chains, silicate grains, building blocks of planets and potentially of life, distributed throughout the universe. The same chemistry that led to life on Earth exists in stellar nurseries across the galaxy, across the universe. The ingredients are common. What combinations lead to biology remains unknown, but the raw materials are everywhere. We are made of matter the universe creates routinely in countless locations. Rosa Pello, a French astronomer studying distant galaxies, considers the cosmological implications. Webb is detecting so many early massive galaxies that we must reconsider galaxy formation timeline. Either stars formed more efficiently than we thought, or dark matter interactions we don't understand accelerated growth, or our cosmological models need revision. Any answer revolutionizes the field. That is what a transformative telescope does. It forces us to rethink everything we thought we understood. Certainty gives way to questions, and questions drive discovery forward. In May 2022, Webb's C3 mirror segment was struck by a micrometeoroid larger than expected from statistical models. Mike Menzel, lead mission systems engineer, recalls the initial panic. Is the mission over? But the team quickly assessed. Actuators can compensate. Image quality reduced only slightly. Science objectives still achievable. Space is not empty. Micrometeoroids constantly bombard any spacecraft. Webb's mirrors must remain exposed, no protective enclosure that would block incoming light. Strikes were anticipated over the decades-long mission. Engineers designed for resilience, for graceful degradation. Webb can tolerate multiple micrometeoroid strikes before science is significantly impacted. After the May 2022 impact, operational procedures changed to avoid pointing toward known meteor stream directions when possible, reducing exposure to higher density regions of micrometeoroid populations. The telescope continues to operate beautifully, continues to collect ancient light, continues to expand human knowledge. One impact among many that will inevitably occur over years of operation, designed for resilience in a hostile environment, built to endure. July 2011 brought a moment of existential crisis for the project. The House Appropriations Committee voted to terminate Webb due to cost overruns. $3 billion had been spent. $7 billion more would be needed. The scientific community mobilized. Thousands of astronomers contacted representatives, emphasized transformational science potential, argued that cancellation would waste already invested funds. Weeks later, the decision was reversed. A close call. We came within weeks of never seeing cosmic dawn, never characterizing exoplanet atmospheres, never peering inside stellar nurseries. John Mather, senior project scientist, reflects on the 3-decade journey. When we started this in the 1990s, none of us had children. Now some of our children have children. We've spent entire careers on this telescope. There were times we thought it would never fly. Congressional near cancellation, technical failures, pandemic. But we persisted because we believed humanity deserved to see cosmic dawn. Generational commitment. Careers devoted to a single instrument. Faith that the work mattered, that the discoveries would be worth the decades of effort. And they were. Amber Strawn, Deputy Project Scientist for Communications, describes Webb's unique vision. Hubble showed us the universe in visible light, what our eyes could see if we were there. Webb shows us the universe in infrared, the heat glow of the cosmos, light stretched by 13 billion years of expansion. It is like gaining a new sense, like a person born without sight, suddenly seeing for the first time. We are seeing what was always there, but invisible to us. The universe reveals dimensions of itself that optical telescopes could never perceive. The photons arriving at Webb's mirror tonight began their journey 13 billion years ago. They traveled through the expanding universe, across cosmic voids, past galaxy clusters, threading through gravitational lenses, finally arriving at L2, where golden mirrors redirect them to detectors cooled colder than outer space itself. Each photon is a messenger from deep time. Each one carries information, wavelengths revealing chemical composition, redshift indicating distance and epoch, intensity suggesting star formation rate. Encoded in light, decoded by instruments, understood by minds. Webb, doesn't rush. Deep field images require 20 hours or more of exposure, sitting motionless, collecting faint photons one by one. Unlike impatient humans checking phones every few minutes, Webb watches with geological patience. There is wisdom in that patience. The universe reveals its secrets slowly to those willing to watch and wait and trust that meaning will emerge from noise. Integration over time transforms random arrivals into clear signal. What appears chaotic becomes ordered. Patience creates understanding. The project began in 1989, launched in 2021, will operate into the 2040s or beyond. It spans generations. Scientists who conceived Webb retired before launch. Early career researchers now using Webb data weren't born when planning began. Children who watched the launch on screens will be conducting their own research using Webb observations years from now. A cathedral built across generations, each one adding to the structure, each one benefiting from predecessors' work. Human achievement that transcends individual lifetimes. Jonathan Gardner, Deputy Senior Project Scientist, describes the mission goals simply. We built Webb to answer: how did the first stars and galaxies form? How do galaxies evolve? How do stars and planetary systems form? And where are the ingredients for life? Within 6 months of operations, Webb had data addressing all 3 questions. 30 years of development, 6 months to begin answering the deepest questions humanity can ask about cosmic origins. That is unprecedented scientific return. That is what vision, perseverance, and collaboration can achieve. Webb orbits in perfect stillness at Lagrange Point 2. Earth, Sun, and Moon aligned in single direction. Sunshield blocking their heat. Mirror collecting ancient light. Instruments analyzing photons older than Earth itself. Radio signals streaming data to ground stations around the planet. A human-built cathedral of knowledge stationed at gravitational balance point, extending human perception 13 billion years into the past. We float here in contemplation of what has been built, what has been learned, what remains to be discovered. Consider what Webb represents beyond the science. Multiple nations collaborating for decades. Thousands of engineers, scientists, technicians, dedicating careers to shared vision. $10 billion invested not in weapons or walls, but in understanding. The telescope stands as testament to what humanity can accomplish when we work together toward knowledge. When we choose curiosity over fear, understanding over ignorance, cooperation over conflict. These choices, sustained over decades, place golden mirrors among the stars. The universe is 13.8 billion years old. For 13.5 of those years, the light now reaching Webb traveled through space. During that journey, Earth formed from dust around a young star. Life emerged in ancient oceans. Evolution produced consciousness capable of wondering about origins. And now that consciousness has built instruments to observe the universe as it was when the light began its journey. We are the universe examining its own history. Made of star stuff, studying stars. Webb watches patiently, as it will for decades more, collecting light from the earliest galaxies, characterizing distant worlds, extending human knowledge one photon at a time. Patient observation matching cosmic timescales. No rush. Just steady accumulation of understanding. The observatory maintains its halo orbit. 800,000 kilometers wide, 6-month period. Perfect gravitational balance, perfect thermal stability, perfect stillness for observation. Cryogenic instruments remain colder than space. 40 Kelvin, 7 Kelvin. Cold enough to hear the universe's faintest whispers. Sensitive enough to detect the heat of a bumblebee at the distance of the moon. "126 actuators maintain mirror alignment. Nanometer precision. Continuous adjustment. Continuous perfection. Active optics ensuring clarity across years of observation. Sunshield provides protection equivalent to SPF 1 million. 300-degree temperature differential. Tennis court size. Hair thickness. Engineering miracle. Photons from cosmic dawn arrive every second. 13 billion-year journeys ending here. Captured by gold. Analyzed by silicon. Understood by carbon-based minds. The first galaxies reveal themselves. 200 million years after the Big Bang. More massive than predicted. More structured than expected. More beautiful than imagined. Star formation observed inside dust clouds. Pillars of creation penetrated. Hundreds of protostars glowing. Stellar nurseries revealed. Birth witnessed. Exoplanet atmospheres characterized. Carbon dioxide detected. Water vapor found. Chemistry of distant worlds. Potential for life assessed. Questions answered. New questions raised. Years from concept to operation. Generational dedication. Vision sustained. Challenges overcome. Success achieved. .344 single-point failures during deployment. All avoided. Perfectly. Perfect execution. Perfect unfolding. engineering triumph. Congressional near cancellation survived. Project preserved. Community mobilized. Funding restored. Vision protected. Micrometeoroid impact absorbed. Actuators compensated. Resilience demonstrated. Operations continued. Science uninterrupted. International collaboration sustained across decades. NASA, ESA, CSA. Thousands of people, multiple nations, shared vision. $10 billion invested in understanding, not in weapons, but in knowledge. Priorities expressed, values demonstrated, humanity at its best. First images released July 12, 2022. World captivated. Deep fields, nebulae, exoplanet spectra, beauty and knowledge combined. Webb operates at wavelengths human eyes cannot perceive. Infrared vision. Heat glow of cosmos. Stretched light from expansion. New sense gained. Gravitational lensing exploited. Galaxy clusters as telescopes. Nature magnifying. Web resolving. Earliest structures revealed. Organic molecules detected in dust clouds. Building blocks of life everywhere. Chemistry common. Ingredients abundant. We are not rare matter. Galaxy formation models revised. Theory meets observation. Assumptions challenged. Understanding deepened. Questions multiply. Hour exposures collected patiently, photon by photon. Signal emerging from noise. Integration over time. Wisdom in patience. Children watched the launch. Will conduct research later. Generational project. Cathedral across time. Legacy building. We are universe examining itself. Consciousness studying origins. Star stuff wondering about stars. Atoms contemplating atoms. Profound recursion. Light travelled 13 billion years. Journey ending at golden mirror. Message from deep time. Information preserved. History revealed. Webb floats in perfect balance. Gravitational equilibrium. Thermal stability. Operational precision. Steady observation. Mission could last 20 years or more. Decades of discovery ahead. Patient watching. Continuous revelation. Knowledge accumulating. We rest now in contemplation of patient observation of light's ancient journey, of human curiosity, of cosmic dawn. Floating at Lagrange Point 2, 1.5 million kilometers from home. Perfect stillness, perfect darkness, perfect peace. The telescope watches, as it will for years, collecting light, revealing universe, extending understanding. Ancient photons arrive, captured and analyzed. Secrets decoded, questions answered, wonder preserved. Breathe with cosmic patience. Inhale the vastness. Exhale into stillness. Rest in the knowledge. Stars surround you. Ancient light bathes you. Perfect darkness. Perfect quiet. Perfect rest. Let your breath slow. Matching Webb's patient rhythm. Observation without hurry. Peace without end. $13 billion years compressed to now. All time present. Past visible. Future unfolding. Rest in this moment. Golden mirrors reflect starlight. Instruments measure. Humans understand. Cosmos reveals. Circle complete. float in perfect balance. Nothing to do, nothing to achieve. Simply observe, simply rest. The universe watches itself through Webb, through you. Consciousness contemplating, awareness aware, being experiencing being. Let thought dissolve like light into darkness. Boundaries fading, separation dissolving. Only presence remains. Breathe the cosmic stillness. Inhale eternity. Exhale into void. Rest in between. Webb continues its vigil, patient and precise. You continue your rest, deep and complete, both perfect in purpose. Ancient light arrives. You rest deeply. Telescope observes. You surrender. Both exactly as should be. Floating in darkness, surrounded by stars, perfectly still, perfectly quiet, perfectly at peace. The vigil continues across years. Your rest deepens across hours. Time becomes irrelevant. cosmic dawn observed, personal night embraced, universe revealing, consciousness releasing. All is well. Sleep now in perfect stillness. Rest completely. Dream peacefully. Float eternally.